Hello and welcome to another IC Monitor tutorial. This video will get you started on integrating your own protocols in the IC Monitor. We'll introduce the tools we have available, namely generic nodes and scripting. We'll use the generic nodes to create a simple protocol. We'll then work with those created nodes and show what the IC Monitor can do with them. We'll set up and enable scripting, examine a simple script, and compare the features of both tools. The IC Monitor offers two powerful tools to integrate proprietary protocols or structured data inside well-known protocols into the IC Monitor for further analysis. Those tools are generic nodes and scripting. If we switch to the Configure tab and look into the Nodes and Scripts group, we'll find the Configure Generic Nodes dialog and the Configure Scripts dialog, which over the course of this Getting Started video will make you familiar with. Now, what are generic nodes? With generic nodes, you can quickly and efficiently describe nested protocol fields. Generic nodes are available in any license. They require no programming skill and can be configured using the graphical user interface and the generic nodes configuration dialog. And generic nodes can be used in the expression language for filters, triggers, or can be made into columns in your Telegram list view. With scripting, on the other hand, users can extend the IC Monitor's functionality a little further. The scripting feature is meant to pick up where generic nodes fall short. You can integrate protocols with dynamic length or variable node length. You can encode your node data with enumerations or node data. You can process protocol data in any way you need, can log it to files or databases, can scale the data, and various other tasks. An API is accessible for scripting, which is limited to protocol and plugin related tasks for security reasons. But for processing the node data, everything that C# script offers is available, and thus you have a lot more flexibility than using just generic nodes. The various tasks are grouped into programming interfaces, and you get class instances to facilitate node-related tasks like data access, node creation, and so on. To demonstrate the features and concepts, we'll pick a couple of fields from the IP protocol out of the TCP/IP stack and recreate them using generic nodes and scripts. Let's start out using generic nodes by opening the generic nodes configuration dialog and adding a root node. Here, we can enter a general description and configure offset and length of our node. Be advised that abbreviations are used in Telegram expressions and must be unique on their level. So if we had a couple more nodes here, they couldn't have equal abbreviations. You can reuse them in lower levels, so if we add a child node, it could have the same abbreviation again. Now down here we specify where the Telegram data is actually located, and we can do that by basing it on a parent node. Now for IP, this is pretty straightforward. We use the Ethernet service data unit, and our data is right in that. We'll also define a filter expression to make sure we only have data when it's actually present in the Ethernet SDU. By setting the condition that ether type needs to be hex 800, we'll only have data in the telegrams that actually contain IP. No need to specify offset and length, as the length is determined by the sum of its child nodes. Now let's create our child nodes. The fields I picked are version, internet header length, TTL, and both IP source and destination. So we'll go ahead and describe our version. And the version is a bit different in that it's not a full byte, but only 4 bits of a byte. So we'll change this to a bit node. We'll have to specify at least the length, but also the offset in this case, which is 4 bits and 4 bits of length. Our next node is the internet header length. We'll also have to switch it to a bits node. It doesn't have an offset, and is 4 bits long. Now note that we completed 1 byte by describing 2 4-bit nodes, and now we have an automatic byte offset of 1. Since we're describing TTL next, we need to change that though. TTL has an offset of 8 bytes and a length of 1. Next is the IP source node. And again, we need to define an offset and a length, and make sure we switch to big endian. IP destination now has the correct offset, since it's the next after IP source. Just need to specify a length and give a general description. So now that we have a couple of nodes, let's go ahead and take them for a test drive. Before we do, let's correct our destination to big endian and hit apply. Now to test our generic nodes, we need a little bit of traffic. So let's get back to capture. Select the capture interface. In this case, the correct one is already selected. And start a live capture. I'm also going to put in some traffic that we can easily identify by just pinging a machine in my network. And that should give us enough traffic to work with. We'll stop the capture and take a look in just a random node that contains the IP protocol. You could make sure of this by entering a display filter. Since most nodes contain it, don't need to bother with that. Now the generic nodes will show up underneath all the other nodes that belong to regular protocols that are embedded in the IC monitor. And you can identify your fields that you entered here by the names you gave them. As we can see, we have version 4, an internet header length of 5, which, if you're familiar with the IP protocol, equals 20, because it has to be multiplied by 4, TTL of hex 40, and 2 IP addresses that we could translate, though they look correct on first glance, as they start with a 10, and that is the address that we pinged. Now as we hover over one of the nodes, we can see they do have a node ID, and they all start with GNS, which is the abbreviation for generic nodes, and underneath that tree we can find our own generic nodes. We could use them in Telegram expressions, and we'll get auto-completion depending on the type and the length of the data that we have here. We don't have any IP telegrams with 0 length, as that would violate the protocol. All of them have a header length of 20, and we can see them now that we applied the display filter. We could use the generic nodes in the Telegram list view as well, and maybe compare if they contain the same value as our regular IP node. And indeed, hex 4 does equal decimal 4, so that's looking good. And if you find telegrams that do not have IP in them, the generic nodes are empty and we don't have any value for our version column. We can use those nodes and their abbreviations in triggers and filters as well, so that gives us quite a lot to work with if we have our own protocol that we want to quickly integrate in the monitor and analyze it. Now let's go ahead and recreate that using scripts. Since activating scripting requires a restart of the IC monitor, we're going to go ahead and save this trace so we can really compare if scripting delivers the same results. Now that that's accomplished, let's go over to scripts. And before we can use scripts, we of course have to enable scripting. And we can now add folders containing scripts. Now note for that, scripts must have their own folder, and its name is going to be used to identify the scripts. And in this folder, there has to be one file named main.cs. So let's go ahead and find a folder to add. We have monitor scripts here, and we could add the top level folder. IC Monitor will then recursively browse and find the containing scripts like so. And we get informed that we'll need a restart and that this folder won't be active until we do. So let's quickly restart the monitor and meet again here. Now after restarting, we get a scripting security warning. This is meant to inform you that scripts are now enabled, and active scripts will be parsed, and even though we only enable an API for node manipulation and plugin tasks in the IC monitor, users can still use CS-script to write harmful code. Now let's head back over to Configure and Scripts. And we now see this folder is active, but our plugin is not yet. Now we see the script is parsed successfully, and we could then enable it. Since scripts are treated like plugins, enabling and disabling a script requires a restart of the monitor. So make sure you always parse your scripts first, and see if they're successful, enable them, and then perform the restart. Once you started the IC monitor with a script that didn't have any errors on the start and was enabled, you can then debug and reload it without having to restart the IC monitor. So let's do the final restart and then have a look at the script. Here we are, back again with the enabled SimpleIP plugin script. Now before we dive into the script itself, let's first have a quick look if it worked. We don't even need to load data for this. We can go over to the Nodes view and find our script as a regular plugin down here. We do have SimpleIP, and it does have internet header length, version, TTL, source and destination, just like our generic nodes. Now to create nodes using scripts, we of course have to write a little bit of CS script code. So let's look into that and learn how we can use C# or CS script to create this SimpleIP protocol and why it's worth the effort compared to generic nodes. Now don't worry, you don't have to start from scratch when designing your own scripts and your own protocols. Just go to the IC Monitor installation directory. There you'll find the directory called References, and in there, example scripts. You can use those example scripts and modify them, and they contain all the necessary using directives and inheritance. Another great source of information is the IC Monitor homepage, and if you own a license and go to the Downloads section, and then to the Documentation, you'll find the Scripting API documentation, which documents all the functions that scripting provides. So you can go in here and find some more information on how to do more complex tasks. Now let's take a look at the code that we need for the SimpleIP protocol. I used the provided IP script and modified it, and at first, because scripts act as plugins, we need some basic information to describe our plugin. That is a name and a description, optionally a version, and an abbreviation. Now the abbreviation has to be unique, and it competes with all the other plugins of the IC Monitor. So you can't use TCP or UDP as your root node. It has to be unique among those as well. Now I specified those in fields, but you're really required to fill out the plugin handler script and provide those attributes. I find it easiest to do this with fields, but of course you could just supply the strings here. The plugin handler script also contains some methods, but as you can see, to start a simple protocol you don't need to implement any of those. They just give you further flexibility to set up local resources, for example with the init plugin function, or do that before the start of Telegram capture, and clean up with closed plugins, among others. The data node provider script has a method called createNodes, and that is where you will create your protocol nodes. The instance of Node Factory that you get in here is used to create all the nodes and configure them. And your first node has to be attached to the provided parent node. Now nodes have a couple of base properties, like a name, short name, an abbreviation that follows the same logic as all the others, and a description. Like generic nodes, we can select the parent by setting a base node. In case of IP, it's again the Ethernet service data unit. And we can also define filter expressions, same as we did with generic nodes. Now we could, like we did with generic nodes, set a fixed length and offset, But using scripts, we have more flexibility. We can do this providing callback functions that dynamically calculate the length of our protocol data, and if necessary, the offset. Though for IP, we can set this to a fixed offset of 0. You can have any combination of fixed offset, fixed length, dynamic offset, and dynamic length that you need. We can also provide functions that determine if the node currently has data or not. We can then create the node using the node factory. We can store nodes as they get returned from the factory. In this case, I want to have the IP main node available for other functions, so I store it. But all these subnodes I don't really need, so I just create them and discard the return. Now before we get to the callback functions that we can supply here, let's take a look at some of the nodes and the configuration options we have. Again, we'll start with the IP header length. And here we have one difference to generic nodes, as we can supply a display format. In this case, it's a decimal, and that'll make it so that once we use the node's data in the IC monitor, it will automatically be displayed as decimal. As with generic nodes, we have to configure that each time manually. We can also provide a dynamic length function, or here we can provide a function that will get the node's data. This function will take the current telegram. We can then extract the data from the telegram, transform it, return our own data, and the IC monitor will then use that as the node's data. The version node is pretty simple, just an offset and a length. And note that we're using bit offset and bit length here, while with the time to live field, we're specifying that information in bytes. Now we don't only have decimal formats, we can also, for example, format data as an IP address, as we do here with our source and destination addresses. We can of course also set our data to be interpreted as big endian, as we did here. Now let's take a look at the callback functions that we supplied, starting here with the header length. If we look into that, this will get called with each telegram that has data for the node. We can then take our stored root node, get its offset, and then identify our data in the telegram using that offset's value. In this case, we only have a couple bits, so I need to shift them out or mask them. And now we can do the calculation for the actual length, which is not the field's value, but the field's value times 4. This way the header will have its actual length, though almost all of the time that will be 20 bytes. We can use that same information to return the value of the length field. If we check out this function, I'll again use the getHeaderLength that we calculate here, transform it to a byte list, and return it. And this will now contain this value as a byte list, and hence the proper data and not just the hex value that is unmultiplied. Now let's go back to the IC monitor and see this protocol in action. We'll have to load our stored capture, and pick a telegram that has IP nodes in it. Now let's clear out the view and make the comparison a little easier. First, we'll take our IP protocol, get the header length, get the TTL, and maybe the source address. Now to compare it, we'll take the same values from the generic nodes, get the header length, get the TTL, and the source. As we can already see, all values from generic nodes are in hex, so we would need to convert them. We could do this either clicking here, or going to the data node column configuration, where we have a little bit more flexibility and maybe can configure all our view at once. Let's find the TTL field, which is here, and also switch that to unsigned decimal. With the IP source address, we're already out of luck though. There's no way to convert that data into an actual IP address. Now if we look into the simple IP that we used from our script, first of all we need a little bit more space, and we can now pull out the header length, the time to live, and our source address. Now as we can see, our scripted version of the protocol pre-formats all the data in a convenient way, and it's pretty much the same data that we have from the IP protocol in the IC monitor. And we have almost all the possibilities that the IC monitor has internally to format or create data ourselves. So scripting is a very powerful tool, though it does require a little bit of programming knowledge and some time spent in the documentation. While generic nodes are a very quick way to get your own protocol in the IC monitor and use it in triggers or display filters or any other task that requires telegram expressions. Now let's clear our view and to recap, take a quick look at the features from generic nodes and scripting. Here's an overview of all the features you might need when creating your own protocols or structured data. It starts, of course, with creating simple nodes with a fixed offset and length, which is possible with generic nodes or scripting. To represent protocols, you need the ability to nest those nodes, meaning parents and children, which also is possible with generic nodes and scripting. To work with the data in the graphical user interface, you need to be able to configure a display format for that data, which to an extent is possible using generic nodes, as you can set a display format for the data in, for example, a Telegram list view. With scripting, you can do it directly with a node and have access to a lot more display formats, and they'll be used in all the graphical user interface views. In some protocols, it's necessary to determine the validity of the node data, which in generic nodes you can do with filter conditions. With scripting, you can provide additional callback functions that examine the node's data, or maybe header fields, to determine if the data is valid. With a lot of protocols, you of course need dynamic offset and length, or have optional fields in the header, which is not possible with generic nodes. You'll need to write a script for that. Scripting also gives you the opportunity to convert units, for example, convert the node's data in degrees Celsius or millivolts, and annotate it. And you can process the node's data using the full feature set of CSScript or C# when you use a script. With generic nodes, you can't access that data. That concludes our intro to creating your own protocols and structured data. There's a lot more, especially to scripting, that you can learn, so watch out for tutorials on those topics on this channel. Thank you for watching, and we'll see each other in the next tutorial.